Hey there, you're in the lab with your mate JJ. Today is Old Book Teardown Day. We're going to have a look at an old book today. Before we get started, I should tell you that my silly job title for today is The Surge Sage. Today I'm the Surge Sage. Surge Sage. That's actually quite difficult to say. Also, firstly, the book we'll be looking at today is the Student Manual for the Art of Electronics. This is obsolete and it has been replaced by Learning the Art of Electronics, which is now in its second edition. Of course, this is the book that we're about to get started on. I've done the introduction. I haven't done the first lab yet. I am trying to get the first lab done. I'm learning heaps of stuff as I do the work for this. At the moment, I'm caught up over here, working my way through Electricity and Magnetism by Purcell and Moring. I'm learning heaps about the physics of electromagnetism, but it's a lot of work. It's taken me a long time. The notes are being written. They're turning up on the on the wiki, on the ITL wiki, so people who have access can have a look at that as they come along. But today it's just a little digression. As I was learning and reading about the art of electronics and learning the art of electronics, I discovered that the second edition of the textbook had this complementary coursework, the student manual. And as I understand it, this particular book was meant to be read in conjunction with the second edition of The Art of Electronics, which is now in its third edition. So this is actually an obsolete book that is supposed to be like a supplement to another book that I don't have. I have the new edition of The Art of Electronics, third edition. I do not have the first edition or the second edition of The Art of Electronics. I would like to get them at some point, just for the sake of the historical value of those books. And that's why I bought this book. I was just interested in it. I wanted to see what the course was like in the olden days. Things do change, particularly digital electronics. That's changed a lot since they would have made this. So yeah, today we're just going to have a quick squiz inside this book, see what's in there, and have a flip through and just see what the course used to look like. Yes, we'll be jumping over to the bench here and we'll be going through the book, and that'll be everything we do in this video. So let's jump over to the bench and get on with it. Here on the bench, this is our book, the Student Manual. It was printed by the university, which perhaps explains this binding. Just looks like it's come straight out of the print shop, doesn't it? They probably printed it themselves. So we'll have a look at the back. Obviously on the front, it's just the title, and this is Hayes and Horowitz. Okay. Hayes, I think, is the main author who's continuing the work, along with another guy now. It's Hayes and Abrams, and now it's just with the assistance of Paul Horowitz for the second edition. So there you go. Now let's have a look at what they say on the back. This manual satisfies two needs for students and teachers using the art of electronics as a text. It sets forth 23 laboratory exercises that can form the backbone of a 1 or 2 semester course in electronics, both analog and digital. Ohm's law through microcomputers. It supplements the text's explanations of selected topics which have been chosen for their importance to a student rather than a practitioner who uses the text as a reference. In 23 units, the manual guides the student through the text, providing, in each case, reading and problem assignments. These break out manageable amounts of information and, very importantly, steer a student toward the material that is essential on a first reading. Tutorials. These are discussions 4 to 15 pages long, explicating topics treated in the relevant text reading. These notes examine a few issues chosen for their importance to a student meeting the subject for the first time. Examples, explanations by analogy to earlier topics, and a great many figures all reinforce the text treatment of this core material. Worked examples. Worked examples follow most tutorials, spelling out not only a solution but also a procedure for solving the sort of problem most important within the scope of the current reading. In addition to these units, the manual includes a reference section which consists of a glossary in which are defined important terms, again supplementing the text index by selecting those, including acronyms and jargon, that are most widely used and likely to puzzle a reader not yet experienced in the field. Review summaries. These contain an outline of the most important topics in each chapter and so help the student to review and organize what has been learned. Data sheets. These representative data sheets allow a student to check specifications against performance observed in the lab and gives practice in hunting for selected information. The manual is a product of many years teaching at Harvard University, where the authors have tested and refined both lab exercises and explanations. The result is a set of course materials tailored to students' needs, moving quickly where appropriate and slowly on those concepts that students have found most difficult. And this has got a little bit of sticker goo on it. Someone's taken a sticker off there. Shall we hit it with the goo on? I don't know. It's a bit sticky and gross. What are we going to do? I'll clean that up quickly. Hang on. All right. So I got that sticker glue cleaned off there, and I don't seem to have damaged the cover. That's good. This seems to have lost a few pages here. Can we fix that? Probably we can. Going on. Let's see if we can. Yeah, okay. Well, I'll do that on time lapse as well. All right, well, that's fixed now too, that binding. So just like I bought one. On we go. And now we're just going to have a look at the table of contents and then have a bit of a flip through and just see what's in here. Hopefully that's all in focus and you can see everything well there. Okay. So it's printed by Cambridge University Press, and this is from 1989. All right. So, here we go. Contents, analog, chapter 1, foundations, DC circuits, class 2, capacitors and RC circuits, a note on reading capacitor values, lab 2 capacitors, okay, class 3 diode circuits, worked example, power supply, lab 3 diode circuits, wrap up chapter 1 review and jargon terms, chapter 2 transistors, bipolar transistors, overview chapters 2 and 3. I suppose when it says chapters, it's referring to which chapters of the textbook, and that would have been for the second edition, I believe. We'll know. Actually, we should probably read the preface before we read these contents here. All right, here's the preface. Just be a second. I'm back. Thought I heard the doorbell, but just must be hearing things. So this is the preface, July 1989, by Hayes and Horowitz. Okay. So there's just the one preface. I assume that there's just been the one edition of this book. And hopefully in the preface it'll tell us which version of the text they used. Oh, I see. It got printed again and again and again until 1999. So this printing must be from 1999. Interesting. Here's their little thing again. They mentioned that in the book still. Cool. All right. Well, we'll have a look in the contents in a second. But before we do, let's have a read of the preface. So I'll just get my coffee out of the way there. How are we doing? Looks pretty good. So, this manual is intended to be used along with The Art of Electronics by Horowitz and Hill, 2nd edition, 1989. There you go. In an introductory electronics course. The manual includes 3 principal elements. Laboratory exercises, 23 of these, each meant to occupy a 3-hour lab period. Each set of laboratory notes, except the last, includes a reading assignment in the text. Explanatory notes, 1 for each laboratory exercise or class. And 3 the worked examples, a total of 20, approximately 1 for each reading assignment. In addition, we have included some reference materials, a glossary of frequently used terms and jargon, review notes for each chapter, noting the most important circuits and topics, selected data sheets, analog and digital. The students this course might suit. These notes arose out of a course at Harvard. They define what we try to teach in that busy term. The course does less than all of Horowitz and Hill, of course. We treat chapters 1 to 11, omitting chapter 7 on precision circuits, which is more specialized than the rest, and skimming over chapter 4 on active filters and oscillators. Even this section includes more information than we expect students to absorb fully on a first pass through the book. This manual tries to guide students to the most important material. The typical student that we see, if there really is a typical student, is an undergraduate majoring in physics and wanting to learn enough electronics to let him or her do useful work in a laboratory. But we do not assume such background in these notes. Students very different from that typical student thrive in our course. Graduate students in the sciences appear regularly. During the summer, we see many high school students, and some of these do brilliantly. Now and then a professor of physics takes the course, and they do all right too. In the extension version of the course, we see lots of programmers who want to know what's going on in their machines, and we see people who just happen to be curious about electronics. That curiosity, in fact, is the only prerequisite for this course and suggests the only good rule to define who will enjoy it. Someone looking for an engineering course will find our treatment oddly informal, but a person eager to learn how to design useful circuits will like this course. Laboratory exercises. The laboratory exercises build upon a set of labs that were set out in the 1981 edition of the Laboratory Manual by Horowitz and Robinson. These new exercises replace all of the original digital labs and substantially revise the analog labs on FETs and oscillators. In the digital section, we have switched over from LSTTL to HCMOS, but the major change has been the enlarged role given to the microprocessor labs and the shift from the Z80 processor programmed rather laboriously via a dip switch dear me, to a 68008 processor programmed through a keyboard. A complete schematic is included, see Lab 15. Complete keypad units are available through the authors, see parts list. We have held to our intention that students should build their computer from the chip level and that they should not be handed a ROM cleverly programmed by someone else. We want our students to feel that they know their computer intimately and that it is fully their product. The digital half of the course now centers on the microcomputer. We meet simpler digital devices, gates, flip-flops, counters, memory, partly because we want to be able to build small digital circuits, but also partly in order to understand the full microcomputer circuit. To put this another way, the final series of labs in which the microcomputer gradually takes from draws together every one of the several circuit elements met earlier: combinational logic networks, flip-flop circuits, counters, memory, and analog digital conversion. The AD conversion experiments have been expanded to include the effects of sampling rate and of filters applied to input and output. Notes. The notes that introduce each lab respond to two needs that students often voice. The notes select a few points from the much broader coverage of the text. Those selected points are, of course, those that we think are most important to a student meeting practical electronics for the first time. The notes explain at length. They do this at a level more basic than the text, and they provide explanations in a step-by-step style that the text cannot afford, given its need to cover far more material. A suggestion: how to use the notes. Here's a proposal. You will, of course, find your own way to use text notes and all the other course materials, but here is one way to begin. Start by reading the day's assignment in the text. It will include some material that is subtler than what we expect you to pick up in the first course. You may want to hear some points restated in another way, or you may want to see an example worked. Primed with this specific sort of curiosity, you might then look at the day's notes and lab, scan first to see which circuits and which points are selected, read the notes on any points that puzzled you. If you still are puzzled, return to the text for a second look at the topics you now know are most important. Skip topics in the notes that you understand already. The notes are meant to help you, not to burden you with additional reading. If you have read and understood the text discussion of a topic, you will miss nothing by omitting the corresponding section in the notes. Try the day's worked example, at least in your head. If it looks easy, you may want to skip it. If it looks hard, probably you should try to do your own solution. If you find yourself heading into a lot of work, especially any involved calculations, probably you are doing unnecessary labor, and it is time to peek at our solution. We hope to teach you an approach to problems of circuit design, not just a set of particular rules. If there is a laborious way and a quick way to reach a good design, we want to push you firmly towards the quick way. We expect that some of these notes will strike you as babyish, some as excessively dense. Your reaction naturally reflects the uneven experience you have had with the topics the text and manual treat. Some of you are sophisticated programmers and will sail through the assembly language programming near the course's end. Others will find it heavy going. That's all right. The course out of which this manual grew, and earlier the text as well, has a reputation as fun and not difficult in one sense, but difficult in another. The concepts are straightforward, abstractions are few, but we do pass a lot of information to our students in a short time. We do expect them to achieve literacy rather fast. This course is a lot like an introductory language course, and we hope to teach by the method sometimes called immersion. It is the laboratory exercises that do the best teaching. We hope the text and this manual will help to make those exercises instructive. Why our figures and text look the way they do. You will discover very quickly that this manual is informal in language and layout. The figures are all hand-drawn. They are done by hand partly because we like the look of hand-drawn figures when they are done right. Not all of our figures are pretty. And partly because we want to encourage students to do their own freehand drafting of schematics. In some cases, we did draft drawings on a computer, then drew the final versions by hand. The text was produced as camera-ready copy,
put out by an ordinary PC word processor. So, as writers used to say long ago, dear reader, look with sympathy, if you can, when you find a typo or a figure drawn amiss. Don't blame the publisher for corporate sloth. Picture instead two fellows hunched over their keyboard and drawing board late at night and beginning to get drowsy. Who helped especially with this book? Two teaching fellows gave us good advice on uncounted occasion. Shan Majid. All right, this is where we'll read the thanks. It's pretty brief. A mathematical physicist who taught with us for years in the Harvard College course, and Steve Moss, a digital engineer who once took the course and then returned to teach. Steve often would linger late into the night helping to try out a new circuit or analyze an old one. Both of these two could perfectly well have taught the course and chose nevertheless to linger. Bodhisvasta, like, I don't know what that is, some sort of reference to, is it, I don't know, giving their expert help in this quieter way. A pair of our former students, Jeff Hobson and Weijing Zhu, helped us first by drawing figures and then gradually turned into this book's godparents, helping in all sorts of ways. Often they would arrive in the evening at the end of a long day's work and then would labor to help us organize, check, recheck, and also to make judgments on how to make our points clearly. Often the end of the workday was defined by the departure of the last bus at 1 a.m. in the morning. Their devotion to the project was invaluable and touching. Finally, Debbie Mills deserves thanks for putting up with her husband Tom's strange long hours, and then toward the end, doing much more, providing essential help in organizing, checking, and correcting the growing stacks of printouts and drawings. Cool. All right, and then we're off to chapter 1. So let's go back and have a look at the contents. And I think they've given us a list of labs here as well. They have, so that's good. We'll read through the list of labs, 23 of them. All right, now we did make a bit of a start on this, but let's start it again. I skipped a bit, so I'll try and read the stuff that's not. I'll just read it. I'll read it. All right. But I do think when it says overview and refers to chapters, I suspect it's referring to the chapters in the book, in the textbook, that is. I'm not sure. Let's jump up to no. Okay, it's the overview for the chapter in this book. Fine. Anyway, let's read it out. We're going to start with the analog section. We've got chapter 1, foundations. Then we have the overview for chapter 1, and then we've got the first class 1, DC circuits, with a worked example, resistors and instruments. Then lab 1, DC circuits. And we've got class 2, capacitors and RC circuits, worked example, RC circuits, a note on reading capacitor values, lab 2, capacitors. Class 3, diode circuits, worked example, power supply, lab 3, diode circuits, wrap up, chapter 1 review, jargon and terms. Chapter 2, transistors, bipolar, overview, chapters 2 and 3. Class 4, transistors 1, first model, worked example, emitter follower, lab 4, transistors 1. Class 5, transistors 2, corrections to the first model, Ebers mol, RE applying this new view. Worked example, common emitter amplifier, bypass emitter, lab 5, transistors 2. Class 6, transistors 3, differential amplifier, Miller effect. Worked example, differential amplifier, lab 6, transistors 3. Wrap up, chapter 2, review, jargon and terms. Chapter 3, field effect transistors. Class 7, FETs 1, linear applications, worked example, current source, source follower. Lab 7, FETs, FETs 1, linear. We return to FETs in Lab 11. Chapter 4, feedback and operational amplifiers. Overview, feedback, chapters 4, 5 and 6. Class 8, op-amps 1, idealized view. Worked examples, inverting amplifier, summing circuit. Lab 8, op amps 1. Class 9, op amps 2, departures from ideal. Worked example, integrators, effects of an op amp error, or effects of op amp errors. Lab 9, op amps 2. Chapter 4, continued. Chapter 5, active filters and oscillators. Class 10, op amps 3, positive feedback, good and bad, comparators, oscillators, and unstable circuits, quantitative view of the effects of negative feedback. Appendix, notes on op amp frequency compensation. Worked example, effects and feedback, quantitative, Schmidt trigger, op amp innards, annotated schematic of the LF411. Lab 10, positive feedback, good and bad. Wrap up, chapters 4 and 5, review, jargon and terms. Chapter 3. All right, that's a bit weird. Why is chapter 3 here? This was chapter 4 and 5. Chapter 3. Okay, that's a bit odd. Chapter 3, field effect transistors revisited. Okay, class 11, FETs. FETs 2, switches, power switching and analog switch applications. Worked example, sample and hold. Lab 11, FET switches. Wrap up, chapter 3, review, jargon and terms. Chapter 6, voltage regulators and power circuits. Class 12, voltage regulators. Lab 12, voltage regulators. Wrap up, chapter 6, jargon and terms. This course omits the text chapter 7, precision circuits and low noise. Okay. This course omits the text chapter 7, precision circuits and low noise techniques. And we've got digital, chapter 8, digital electronics. Overview, chapters 8 and 9. Class 13, digital gates, combinational logic, work examples, multiplexers, binary arithmetic. Lab 13, digital gates. Class 14, sequential circuits, flip-flops, worked example, combinational logic. Lab 14, flip-flops. Class 15, counters, worked example, counter examples. Lab 15, counters. Class 16, memory, buses, state machines. Worked example, state machines. Lab 16, memory and state machines. Wrap up, chapter 8, review, jargon and terms. Chapter 9, digital meets analog. Class 17, analog to and from digital. Phase locked loop. Lab 17, analog to and from digital. Phase locked loop. Wrap up, chapter 9, review, jargon and terms. Chapters 10 and 11, microcomputers and microprocessors. Overview, chapters 10 and 11. Class 18, MU1, IBM PC and our lab microcomputer. Worked example, minimal 68008 controller. Lab 18, add CPU. Class 19, assembly language, inside the CPU, I/O decoding, supplementary notes, introduction to assembly language. Lab 19, MU2, I/O. Class 20, MU3, AD to and from DA, interfacing, masks, data tables. Lab 20, subroutines, more I/O programming. Class 21, MU4, more assembly language programming, 12-bit port. Worked example, 10 tiny programs. Worked example, 12-bit frequency counter. Hand assembly, table of codes. Lab 21, AD and DA, data handling. Class 22, MU5, interrupts and other exceptions. Debugging aid, register clock in 2 forms. Lab 22, storage scope, interrupts and other exceptions. Class 23, MU6, wrap up. Buying and building. Lab 23, applying your microcomputer. Toy catalog. Wrap up, chapters 10, 11. Review, jargon and terms. Appendix, okay, so there's 4 appendices. Appendix A, equipment and parts list. Appendix B, selected data sheets for the 2N5485 JFET, for the DG403 analog switch, for the 74HC74 dual D flip-flop, the AD75698 8-bit AD and DA, 68008 execution times and timing diagram, 25120 write-only memory. Appendix C, big picture schematic of lab microcomputer. Appendix D, pinouts. And we've got an index starting on page 612. And then this is the list of labs. So let's have a read of the list of labs. This is part 1, analog labs. Lab 1, DC circuits. Ohm's law, a nonlinear device, the diode, voltage divider, Thevenin model, oscilloscope, AC voltage divider. Lab 2, capacitors, RC circuit, differentiator, integrator, low pass filter, high pass filter, filter example 1, filter example 2, blocking capacitor, and LC filter. Lab 3, diodes, LC resonance circuit, confirming Fourier series, half-wave rectifier, full-wave bridge rectifier, ripple, signal diodes, diode clamp, diode limiter, impedances of test instruments. Lab 4, transistors 1. Transistor junctions are diodes, emitter follower, transistor current gain, current source, common emitter amplifier, and transistor switch. Lab 5, transistors 2, dynamic diode curve tracer, grounded emitter amplifier, current mirror, Ebers mole equation, biasing, good and bad, push-pull. Lab 6, transistors 3, differential amplifier, bootstrap, Miller effect, Darlington, superbeta. Lab 7, field effect transistors 1. FET characteristics, FET current sources, source follower, FET as voltage controlled resistance, amplitude modulation, radio broadcast. Lab 8, op amps 1, op amp open loop gain, inverting amplifier, non-inverting amplifier, follower, current source, current to voltage converter, summing amplifier, push-pull buffer. Lab 9, op amps 2, op amp limitations, AC amplifier, integrator, differentiator, active rectifier, active clamp. Lab 10, oscillators, comparator, Schmidt trigger, IC relaxation oscillator, sawtooth wave oscillator, voltage controlled oscillator, wine bridge, sine oscillator, unwanted oscillations, discrete follower, and op amp stability problems. Lab 11, field effect transistors 2, analog switch characteristics, applications, chopper circuit, sample and hold, switch capacitor filters, negative voltage from positive. Lab 12, power supplies, the 723 regulator, 3-terminal fixed regulator, 3-terminal adjustable regulator, 3-terminal regulator as current source, voltage reference, crowbar clamp. Part 2, digital labs. Lab 13, gates, logic probe, IC gates, TTL and CMOS, logic functions with NAND, gate innards, TTL, CMOS, CMOS not NAND, 3-state. Lab 14, flip-flops, latch, D-flop, JK flop, ripple counter, synchronous counter, shift register, digitally timed one-shot. Lab 15, counters, 8-bit counter, cascading, load from keyboard, programmable divide by n counter, period meter, capacitance meter. Lab 16, memory, state machines, RAM, divide by 3, your design, memory-based state machines, single loop, external control added. Lab 17, AD, phase lock loop, 2 digital feedback machines, DA and AD. Slow motion, full speed, displaying search tree, speed limit, latching output, phase lock loop, frequency multiplier. Lab 18, Mu1, adding CPU, clock, CPU preliminary test, fixing bugs grant. There's an asterisk here, I'm not sure what that refers to. Memory enable logic, memory write logic, single step, test program, full speed, timing example. Lab 19, Mu2, I/O, output, first small programs, battery backup, power fail detector, I/O decoder, data displays, timing program. Lab 20, Mu3, input, more small programs, delay as subroutine, improved delay routines, input hardware, data input hardware, input output program, ready signal, I/O program with enter ready function, decimal arithmetic. Lab 21, move 4, AD to and from DA, AD to DA wiring details, programs confirming that DA's AD work, in and out, invert, rectify, low pass. Lab 22, move 5, storage scope, interrupts and other exceptions, storage scope, keyboard control, exceptions, a software exception, illegal, interrupt hardware to request interrupt. Okay, hardware to request interrupt. Program, main and service routine, NMI, applying interrupts. Register check, a debugging aid. Optional program, install if you choose to. Lab 23, applying your microcomputer. Toy catalog, XY scope displays, light pen, voice output, driving a stepper motor, games, sound sampling / generation. All right. And off we go. This is chapter 1 overview. The title of this first chapter, Foundations, describes its place pretty well. Here you will learn techniques that will underlie circuitry that later produces impressive results. Chapter 1's circuits are humbler than you will see later, and the devices you meet here are probably more familiar to you than, say, transistors, operational amplifiers, or microprocessors. Ohm's law will surprise none of you. I equals C to V to T probably sounds at least vaguely familiar, but the circuit elements that this chapter treats, passive devices, appear over and over in later active circuits. So if a student happens to tell us, I'm going to be on the day you're doing lab 2, we tell them he will have to make it up the course somehow. All right. It's actually quite similar to the introduction in the latest book. All right, we're off. So this is the first class on DC circuits. So this is Kirchhoff's current law and voltage law. The sum around the circuit is 0 for voltage, and the current in equals the current out. Some rules about transistors in parallel and series. In parallel, the small resistor dominates, and in series, the large resistor dominates. Cool. And I've got a voltage divider here. I'm just looking at output impedance, which is the load. Design rule of thumb. When circuit A drives circuit B, let R out for A be less than or equal to 1/10 of R in for B. So here's a worked example. Modify a meter movement to form a voltmeter and ammeter. That sounds kind of interesting, doesn't it? Thevenin models. Some of these examples show typical difficulties that can slow you down until you have done a lot of Thevenin models. The leftmost circuit is most easily done by temporarily redefining ground. That trick puts the circuit into entirely familiar form. I see. They add 5 volts to everything, just bump it all up. Yeah, all right. Effects of loading. This example recapitulates a point made several times over the first day's class notes. As you recognize, reminder, the ohms per volt rating implies that on the 1 volt scale, that is when 1 volt causes full deflection of the meter will present that input resistance. What resistance would the meter present when set to the 10 volt scale? Okay. And then we've got our lab for DC circuits, which is actually the lab that I really need to get on with recording for my Learning the Art of Electronics project. I already had a couple of goes at it actually, but it took a long time. I think it uses 7.5 and 15k ohm resistors. It probably hasn't changed. Oh no, it's 1k there. I think they did change it. This is saying 10k and 5k. We're using 15 and 7.5. So this is class 2, which is capacitors and RC circuits. Chapter 1, worked examples, RC circuits. They're very good at their hand-drawn schematics. They're very neat. A note on reading capacitor values. All right. It's a bit of a dark art, the old capacitors. The resistors are much more consistent or easy. All right, this is our second lab, capacitors. We're going to learn about capacitors in our second lab here. It's great. Then we've got class 3, diode circuits. Okay, so we're doing diodes third. We've done resistors, capacitors, and diodes. This is our bridge rectifier. Then we've got Zener diodes. Chapter 1, worked example, power supply. Oh, cool. Make a power supply. We've got a transformer in the power supply there. Very good. Lab 3, diode circuits. All right. Half-wave rectifier, full-wave rectifier. They were mentioned already. Impedance of test instruments. Review, important topics. All right. Important topics. 1, resistive circuits. A, voltage dividers. B, R out, Z out, R in, Z out. I think it means Z in, doesn't it? And Thevenin models. 2, RC circuits. A, generally. 1, time domain versus frequency domain. 2, step response versus sign response. B, important RC circuits. 1, integrator, differentiator. Either can be described as a filter that is murdering signal. Gee, that's strong language. 2, filters. 1, F3 to B. 2, phase shift. And 3, phases. Only an optional aid to visualizing what's going on. 3, diode circuits. A, rectifiers. B, clamp. C, Zener voltage reference. D, power supply. 1, ripple. 2, transformer rating, RMS. 3, current ratings, fuse and transformer. 4, LC circuits. Rare in this course, 1 LC resonance circuit, lab 3, but they haunt us as an unwanted effect of stray inductance and capacitance, ringing in circuits, oscillation in a follower, for example, see unwanted oscillations in lab 10. All right, then we've got some jargon and terms. Choke is an inductor. Droop, the fall of voltage as effect of loading. Loading implies drawing of current. Primary, input winding of transformer. Ripple, Variation of voltage resulting from partial discharge of power supply filter capacitor between rechargings by the transformer. Rise time. The time for waveform to rise from 10% to final value of 90%. RMS. Root mean of squares. Used to describe power delivered by time varying waveform. For sine, V RMS equals V peak divided by the square root of 2. The secondary is the output winding of a transformer. Stiff of a voltage source means it droops little under load. Okay, so it's stiff if it doesn't droop. All right, V peak equals amplitude. For example, in Vt equals A sine omega t, A is peak voltage, see figure 117 and page 16. And then V peak to peak, VPP. Another way to characterize the size of a waveform, much less common than V peak. Right. All right, now we're up to chapters 2 and 3. I think it's referring to chapters 2 and 3 of the textbook. That's my guess. Not real sure. A bit confused. Oh man. So, a novel and powerful new sort of circuit performance appears in this chapter. A circuit that can amplify. Sometimes the circuit will amplify voltage. That's what most people think of as an amplifier's job. Sometimes the circuit will amplify only current. In that event, one can describe its amplification as a transformation of impedances. As you know from your work in chapter 1, that is a valuable trick. The transistors introduced in this chapter are called bipolar because the charge carrying mechanism uses carrier of both polarities, but that is a story for another course. In the chapter that follows, you will meet the other sort of transistor, which is called field effect rather than unipolar, although they were called unipolar at first. The FET type was developed later, but has turned out to be more important than bipolar in digital devices. You will see much of these FET logic circuits later in this course. In analog circuits, bipolar transistors still dominate, but even their FETs are gaining. All right. There. Okay, okay, so the model of a transistor is as a valve. It's not a pump, it's a valve. All right. So, worked example, emitter follower. The text works a similar problem in detail. The example below differs in describing an AC follower. That makes a difference, as you will see, but the problems are otherwise very similar. Okay. Lab 4, transistors 1. Here is a method for spot checking a suspected bad transistor. The transistor must look like a pair of diodes when you test each junction separately. But caution, do not take this as a description of the transistor's mechanism when it is operating. It does not behave like two back-to-back diodes when operating. The following circuit made with a pair of diodes would be a flop indeed. Okay, we even got a little smiley there. Oh, is it a smiley or is it, I don't know, maybe it's just a colon. All right, so we're off. Emitter follower, current source. Construct the current source shown above, sometimes called more exactly a current sink. All right. Slowly vary the 10K variable load and look for changes in current measured by the VOM. What happens at maximum resistance? Can you explain in terms of voltage compliance of the current source? Transistor switch. Class 5, transistors 2. Corrections to the first model, Ebers mol RE, applying this new view. Topics, old and new. Alright. Shall we have a look? The old topics were our first transistor model, simple IC equals beta times IB. Simpler IC approximately equals IEV, BE is 0.6 volts. New, transistor is controlled by VBE, Ebers mol view. Applications, circuits that baffle earlier view, current mirror, common emitter amp with no RE, R out, a follower driven by R source of moderate value. Complications, temperature effects, and the early, is it the early effect or the Ely effect? I don't know, I should know, I'll find out. Okay, so it is the early effect, and it is named after a person. Their name was Early. There you go, just like being early, arriving on time sort of thing, or before time. All right, so now we know how to pronounce early effect. We learned something. Just playing around with transistors here. Temperature effects. Semiconductor junctions respond so vigorously to temperature changes that they often are used as temperature sensors. There you go. Here's the early effect. Here is a picture of this effect, which just describes the transistor's departure from the ideal view that it is a current source. Early effect. IC is determined, say both of our transistor models determined by IB or VB, but VCE does matter a little, says Early. IC grows with VCE as if CE were a very large resistance. A transistor is a pretty good current source, but it also acts a little like a resistor. Indeed, transistor is from the words transfer resistor. So there you go. The current IC grows as the voltage across the device grows. Okay. So this is the early effect. The change in the base to emitter voltage equals negative alpha times the change in the voltage across the collector and the emitter, where alpha is approximately 10 to the minus 4. IC is assumed constant. Okay. All right. Chapter 2, worked example, common emitter amplifier. Lab 5, transistors 2. More about transistors. Matched transistors. Ebers mol equation. Biasing, good and bad. Push-pull. Class 6, transistors 3, differential amp. Common mode gain. Miller effect. In an inverting amplifier, the small capacitance between input and output, the base and collector for a common emitter amplifier, is effectively enlarged by circuit gain so that it behaves like a capacitance of 1 plus gain times as large going to ground. Miller noticed that the small capacitance between the collector and the base of a few picofarads acts like a capacitance 1 plus gain times as big as the capacitance from the collector to the base, connected between the base and ground. Since that cap to ground and R source form a low-pass filter, high frequencies lose and they begin to lose at an F3 to B lots lower, that is 1 plus gain times lower than F3 to B without the Miller effect. Chapter 2, worked example, differential amplifier. All right. Transistors 2. Differential amplifier there again. Yeah. Chapter review, chapter 2, important topics and circuits. Generally, ground rules, preconditions assumed, 2 modes, current amp with beta and voltage amp with Ebers mol. Biasing, design rules, set voltage at base, not current. Important circuits, switch. Here with transistor saturated, usual beta rule does not apply. Input current is typically about 10 times B. Follower, impedance changing. Here is one of the few cases where you need to use beta in your calculations, but a worst case beta. Push-pull, a variation. Common emitter amplifier, degenerated emitter resistor. Excuse me for a sec. It's a degenerated emitter resistor, an early view of feedback. Distortion, agreed for gain. Current source, current mirror. Differential amplifier, important for several reasons. It's the guts of any op-amp. It's inherently temperature compensated, though not in tail current source. Can beat Miller effect. General problems revisited. Temperature effects, remedies, compensation, for example, a mirror or a differential amp. RE as feedback, e.g. degenerated emitter, common emitter amp. Okay. Early effect remedies, Wilson mirror, RE. Miller effect remedies, cascode and differential. Okay, jargon and terms. Biasing, bootstrap, bypassed, cascode, clipping, cascode. A circuit that uses one transistor to buffer or isolate another from voltage variation so as to improve performance of the protected transistor. Used in cascode amplifier to beat the Miller effect, in current source to beat the early effect. Clipping, compliance, early effect. With early effect again is the variation of input, the current on the collector with the voltage through the collector and the emitter. Thus, it describes transistors' departure from true current source behavior. Okay. So the current varies with the voltage. Emitter degeneration, impedance looking in a direction. Impedance at a point considering only the circuit's elements lying in one direction or another. Example, at transistor's base, impedance looking back, one sees BIOS driver and R source. Looking into the base, one only sees beta times RE. All right. Miller effect, quiescent current or quiescent voltage. Split supplies, power supplies of both polarities, negative as well as positive, used in contrast to single supply. Interesting. Transconductance and Wilson mirror. Lots to learn. Chapter 3, Class 7, FETs 1. FET types. We concentrate on N-channel. 2 distinctions within this category. The J-FET, the junction FET, versus the MOSFET, which is an insulated gate FET. Depletion mode. All J-FETs, occasional MOSFETs, versus enhancement mode. Most MOSFETs, no J-FETs. Oh, interesting. Applications: current source, follower, voltage controlled resistance, less important. Why FETs? We use them because they can do some jobs better than bipolar transistors. Consider FETs when you want a very high input impedance, a bidirectional analog switch, a simple current source, 2-terminal, a voltage controlled resistance. But the first of these FET virtues are by far the most important. Enormous input impedance. Right. That means that they end up using less power, so they can process information as voltages and not get caught up drawing currents. All right, we're going to talk about how the depletion mode and the enhancement mode FETs work. We're going to talk about current sources, limitations, gain, FET versus bipolar. Okay. So a FET's gain is lower than bipolar transistors. There you go. Chapter 7, worked example, current source, source follower. Lab 7, FETs 1, first view. FET as a variable resistor. Chapters 4, 5, and 6, feedback, op amps, oscillators, power supplies. Overview. What are we looking at here? Harold Black's notes on the feed-forward amplifier, conceived as he rode the ferry from Staten Island to work one summer morning in 1927. Copyright 1977, the IEEE, reprinted with permission from Harold S. Black, Inventing the Negative Feedback Amplifier, IEEE Spectrum, December 1977. He's literally made some notes on the newspaper by the looks of it. Huh. Isn't that funny? A piece of advice, unsolicited. How to get the greatest satisfaction out of the feedback circuits you are about to meet. Here are 2 thoughts that may help you enjoy these circuits. As you work with an op-amp circuit, recall the equivalent circuit made without feedback and the difficulties it presented. For example, the transistor follower, both bipolar and FET, or the transistor current sources. The op-amp versions in general will work better to an extent that should astonish you. Okay. All right. Class 8, op-amps, idealized view. Examples of feedback without op-amps. Op-amp golden rules. 1. The output attempts to do whatever is necessary to make the voltage difference between the two inputs 0. The inputs draw no current. Oh, that's interesting. When do the golden rules apply? Strange things can be put into feedback loop. All right. Worked examples, op-amps idealized. Lab 8, op-amps 1. We're working with the LF411. It's an 8-pin IC. Phototransistor circuit. Push-pull buffer. Class 9, op-amps 2, departures from ideal. Working with op amps here. Oh, that's pretty complicated. What are we looking at there? Inside the 411 schematic, simplified and detailed. All right, this is the detailed schematic of the inside of that integrated circuit that we've been using. Here we learn the 741, cool, and the LF411. Lab circuit uses high gain DC amp to make errors measurable. I think all of these integrated circuits are probably not recommended by now. They're old. Worked examples, integrators, imperfect op amps. I go up to lab 9, op amps 2. Here's the integrator and a differentiator. Isn't that fun? Active rectifier. Improved. Chapter 4 continued, and Chapter 5. Class 10, positive feedback, good and bad, comparators, oscillators, and unstable circuits, a quantitative view of the effects of negative feedback. All right, there's a lot of topics going to be covered in this chapter. Class number 10. Yeah, that's a big class. All right, we've got an appendix here, op amp frequency compensation. Worked examples, effects of feedback. Worked examples, the Schmidt trigger. Chapter 4, op amp innards. Oh wow, this is great fun. Check that out. This is the LF411 schematic again, but this time it's annotated. Wow. There's a lot there. We won't go through it all. Pretty interesting though. A lot of transistors in there, and they're all bipolar. No FET. RC oscillator, 555 oscillator. Good old 555, huh? Wire bridge. Unwanted oscillations. Low pass filter. Review of important topics. All right. So, operational amplifiers and feedback. Generally, A, feedback as a general technique versus use with op amps. B, idealized view of op amps, the golden rules. 2, important circuits. Do you remember the golden rules, by the way? I remember one of them is it tries to make its inputs 0. I forget the other one. Important circuits, negative feedback, amplifiers, non-inverting, AC and DC, inverting, incidental virtual ground or summing junction, integrator, ideal but usually compromised for stability, differentiator, always compromised for stability, active versions of other familiar circuits, current source, push-pull, rectifier, clamp. B, positive feedback. 1, Schmidt trigger. 2, relaxation oscillator. C, circuits using both positive and negative feedback. 1, NIC. 2, oscillators. 1, relaxation oscillator. 2, wire bridge, sine, gain control. 3, generally, again, a second view, departures from ideal. A, important op amp characteristics or imperfections. VOS, current bias, IOS, frequency limits, FT, slew rate, and B, stability or compensation. Chapter 4, jargon and terms. Bias current, frequency compensation, hysteresis, offset current, offset voltage, slew rate, saturation, Schmidt trigger, summing junction, trans resistance amplifier, and virtual ground. That was a big chapter. Chapter 3 revisited, class 11, FETs 2, switches. Okay, looking at FETs again, having just looked at bipolar transistors in amplifiers. Worked examples, sample and hold. Fancier sample and holds. Okay. Lab 11. FETs 2, FET switches. Looking at the power MOSFET. This is the saturation characteristic of a small bipolar power transistor. We'll put the VCE against the IC. CMOS analog switches. Chapter 3 review. Important topics and circuits. Generally, A. FETs versus bipolar. B. FET mechanism, a peak within, helps one distinguish. 1. Depletion mode, includes all JFETs versus enhancement mode. This is the usual form of a MOSFET switch. 2. JFET versus MOSFET. JFET better as input stage of op amps, good for current sources. MOSFET better as a switch, universal in logic, where CMOS, P and N channel types combined, is most elegant. Right. 2. Important circuits. A. Follower. 1. Characteristics versus bipolar follower. 1. Rn and Zin. 2. Attenuation. 3. R out. B. Current source can be simple, 2 terminal, also nice when combined with op amp. Variable resistor. Switch. 1. Power. The input impedance is gigantic at DC, but considerable capacitance as a switch for the FET, I guess. Analog applications, sample and hold, multiplexer, switch capacitor, filter. Jargon and terms, acquisition time, body, charge injection, CISS, COSS, depletion mode, droop rate, enhancement mode, feed through, IDSS, JFET, latch up, linear region, MOSFET, RON, or R on, sample and hold, saturation, substrate, transconductance, GM, VGS minus VT, VP, and VT. Chapter 6, Class 12, voltage regulators. All right. Different schemes, switching regulators, Lab 12, voltage regulators. Are we making them or using them? I think we're using them. Crowbar over voltage protection. Jargon and terms, crowbar, dropout voltage, SCR, which is of course the silicon controlled rectifier, and a slow blow fuse. Chapter 8, chapters 8 and 9, digital electronics overview. Digital gates, combinational logic. I'm just going to jump back a bit. I want to read out the definition of the crowbar. It's an over-voltage protection circuit. Shorts the supply output to ground when excessive voltage is detected. It remains shorted until reset if done, as usual, with an SCR. Okay, there you go. De Morgan's theorem. Oh, isn't that fun? They've shown it in pictorial form. Yeah. So that's is that XOR? I think it is. Is that XOR? Or maybe it's just OR. Yeah, it's just OR. Okay. So you input and you negate them, or you AND them and you negate the result. Worked example, multiplexers. I've seen this drawing before. It's the Ministry of Truth choosing who they're going to listen to. Binary arithmetic, worked examples. ALU, the arithmetic logic unit. Digital gates. And there's lots to know, isn't there? CMOS 3-state. Class 14, sequential circuits, flip-flops. Worked examples, combinational logic. Lab 14, flip-flops. JK type. JK encounter, ripple and synchronous counters, synchronous counter, switch bounce. Class 15, counters. Counters from flip-flops. Divide by N counter. Digital voltmeter. Digital capacitance meter. Chapter 8, worked examples, counter use. Lab 15, counters. Note, the keypad is not a standard commercial part. It can be made up from the schematic attached to these lab notes, or it can be ordered in complete form. See the parts list for ordering information. Looks like we're not using a 7-segment display. Looks like we're making one out of dots. Capacitance meter. Elements of today's circuit. Private breadboard keypad. Keypad and pinout functions. Interesting. Class 16, memory, buses and state machines. This paper is actually quite thick paper. Feels like 2 sheets, but it's only 1 sheet. Worked examples, state machines. Lab 16, Memory and State Machines. Chapter 8, Review, Important Topics. Some general ideas. Boolean manipulation. De Morgan's theorem, the most important non-obvious notion. Active low and assertion level symbol cause confusion, but useful and easy if you relax and don't fight them. B, hardware gate properties. Inputs, TTL versus CMOS. Impedance, what floated inputs do. Outputs, TTL versus CMOS. 3-state, open collector. Rare except in comparators where it is standard. Devices, combinational devices. Gates, just a few standard functions and or not XOR and the complemented output versions. Larger building blocks include the multiplexer, decoder, encoder, and adder. Sequential devices, flip-flops, D, SR, and JK. Flops combined, shift register, counters, ripple counters, synchronous counters, loadable synchronous counter, up-down synchronous counter. State machines, a generalization of counter can be made with gating and flops or with ROM and flops. One shot sequential, RC timed, which is usual, and digitally timed, good if a clock is at hand. Ripper. Then we've got a bunch of jargon. Look at this. Active high or active low, assert, assertion level symbol, asynchronous, clear, combinational, decoder, edge triggered, enable, float, flop, hold time, jam clear, jam load, latch, load, multiplexer, one shot, preset, propagation delay, register, reset, ripple counter, sequential, set, setup time, shift register, state, state machine, synchronous, 3-state, tri-state, and then we're up to chapter 9, which is analog to and from digital and the phase-locked loop. And off we go, learning about digital to analog and analog to digital. Sticky pages here. There we go. All right, we're up to lab 17, analog to digital and back again, phase-locked loop. Okay. Specific advice. 9.03, interfacing between families. I think this is referring to the book. I really should get myself a copy of the second edition, just for the sake of antiquity. Analog to digital converter, digital to analog converter, analog to digital, watching the conversion process, slow motion checkout, operation at normal speed, speed limit, completing the AD, latching and digital output, phase locked loop, a lot of words there. Okay, this is chapter 9, jargon and terms. ADC, aliasing, binary search, capture range, DAC, dual slope converter, flash AD, lock range, Nyquist theorem, and SAR, successive approximation register. Chapters 10 and 11, microcomputers and microprocessors, overview. As we reach computers, we reach a subject that in one sense is familiar to most students. Practically everyone these days has done some programming, and some of you no doubt are sophisticated in the subject. But in another sense, computers, as we view them in this course, may be new even to an experienced programmer. We take a worms level view of the machines, concentrating on hardware and thinking about hardware even when we do program. So these chapters on microcomputers should confirm the digital hardware learning that you have been engaged in since Lab 13. Class 18, MU1, IBM PC, and our Lab Micro. Oh, when it says MU1, it means like microcontroller or microcomputer. Chapter 11, worked example, minimal 68008 controller. I don't know how people call that. Do they call it 68008 or do they call it 68008? I don't know. Lab 18, Micro 1, add CPU. Big picture. Wow, look at that. Today's changes and additions. The computer evolves from RAM to a counter circuit. All right. Yeah. Not sure what that star is all about. I haven't really figured that out. Test program. Huh. Assembly language inside the CPU. Input-output decoding. Assembly language. Notes and examples. This is the computer that we're slowly putting together. Wow. Using a particular chip. One chip, analog to digital and digital to analog package. All right. Subroutines. This is the AD7569. One chip. Digital to analog and analog to digital, 8 bits. All right, micro 3, subroutines, more I/O programming. Invoking delay as a subroutine. Micro 4, more assembly language programming, 12-bit port. All right. Worked examples, assembly language, 10 tiny programs. All right. In and out, invert, full wave rectifier. Half wave rectifier, low pass filter. That's interesting. So you could do a low pass filter in software. Here we need to form an average each time around the loop between the new sample and the previous average. We want to give old and new equal weight so we can add and divide by 2, or perhaps divide by 2 and then add. The general scheme is clear enough. It's the details that get sticky as usual. Does it matter whether we add first, divide second, or vice versa? Should we use 68,000 divide instruction? Let's start by doing it slightly wrong just to appreciate what's at stake. Tom did it wrong, first try in the lab. We don't want to be too ludicrously wrong though. We don't want to use the divide instruction, which takes 144 clocks. Instead, we can divide by 2 very fast with a shift rotation operation. Here goes. All right, now we've got some assembly instructions here. Faulty low-pass filter program. What's wrong with that? LSR, logical shift right, brings a 0. I'm just going to make more coffee. All right, so they're obviously going through the program here, and they're going to explain why it's wrong, and we're not going to look that closely at it. It is sad, I think, that we're probably doing less assembly language stuff in the new iteration of this work. I think it's more C programming, which is fair enough, but I would like to learn a bit more about assembly, although it is quite tedious, isn't it? Check it out. Wow. All right, now we're up to chapter 11, worked example, the 68,000. Is it 68008? I don't know how you pronounce it still. Frequency counter. Okay, that's interesting. Hand assembly. Hand assembly. At first glance, the task of assembling 68,000 code may look hopeless. Doesn't a 16-bit instruction word imply 64K possible codes? And weren't assemblers developed just to take this horrible work off human shoulders? Yes, we don't propose that you do much assembly of code by hand, but we have found that for tiny programs, hand assembly is faster than the use of an assembler. Some overhead gets in the way of assembling a very small program. You have to go to the computer, type in code, invoke the assembler, print. That takes longer than writing a 6-line program by hand. And whenever someone sits down in front of a computer, the person runs the risk of getting drawn into the entertaining but time-gobbling game of trying small improvements, revising some more. That process is appropriate to a programming course, but not in a course that tries to keep your attention close to the hardware side of your own little computer. There's a note here. In case the notion of assembly isn't quite clear to you, it means simply finding the machine code equivalent to the mnemonic, discovering that the hex code for MOV BDOD1 is 1200. It also includes the conversion of labels, convenient for human readers, into addresses, absolute or relative, which the computer requires. All right. Wow. Huh. Lab 21, Micro 4, analog to digital, digital to analog, data handling. Wow. Using phase lock loop to adjust F3 to B to sample rate. Class 22, Micro 5, interrupts and other exceptions. A debugging aid, register check, 2 versions. 2 versions of register check, baby check and register check. These two programs can help you debug a program, but you should feel free to ignore these notes if you like. If you are feeling pressed for time and extremely eager to get on with your own programming, rush on. Don't feel obliged to even read this handout. Okay, Baby Check is a primitive version. Register Check, a fancier version, but they do essentially the same thing. They allow you to discover the values of all the CPU registers at any point in your program. Baby Check is very easy to enter. It's a 3-line program. Register Check takes perhaps half an hour to enter and check. It's about 100 lines long. It also requires that you wire the second of the 2 ready keys shown in the circuit big picture. Register Check can reward you for the harder work, however. This longer program lets you discover register values while the program runs using the keypad. Type D2 to discover the word length value of D2. Type A7 to get the value of the stack pointer, and so on. It lets you do this as you move through a program as slowly as you like, one instruction at a time. Baby Check, in contrast, lets you discover register values by taking the bus and walking through the stack, looking at the stored values. You'll need a pencil and paper to help you keep track of what register you're looking at. Okay. Okay. So it basically just pushes the registers onto the stack. Right. And then this is the monstrous register check. Looking forward to seeing the code for that. Here it is. Wow. This routine evokes any of the registers plus program counter and SR. I'm not sure what that is. Stack maybe, I don't know. Using the keypad. AX evokes contents of that address register. DX gets the data register. FX gets flags, status register. Anything else gets program counter. Values limited to word size to fit displays. As written, expects to be reached through an exception vector. PC and CR evocation depend on that assumption. To invoke this as a response to trace, turn on trace by ORing 8000 with SR in PGM to be traced. Register use. Okay. Lab 22, Micro 5, storage scope, interrupts and other exceptions. Using a moving pointer, a storage scope. End of table tests, optional, fun. Use storage scope to record sound. Alright, okay. Keyboard control, optional. Fancier version, exceptions. A software exception, illegal instruction. A hardware exception, an interrupt. Hardware to request interrupt. Interrupt response. Programs main and service routine. Interrupt test programs. Using interrupts. When you are satisfied that your interrupt hardware works satisfactorily, you should apply it to a problem that requires the quick response interrupts allow. You might try the switch bounce capture. The storage scope loaded promptly upon the beginning of bounce. Class 23, Micro 6, wrap up. Buying and building. An inventory of your bag of tricks, a tree. That's a bit of fun. Lab 23, this is the last lab. Micro 6, applying your microcontroller, toy catalog. True vector drawing, position relative. Oh, that's interesting. Yeah, right. I think they used to have true like vector graphics with cathode ray tubes that would literally trace out an XY like line. I think that was contemporary back in the video games era of like the late 70s or the early 80s. I don't really know. Stepper motor. Drawing machine. Little computer meets the PC. Processing stored inputs, making noises. You can make some pretty ugly noises by using your computer to drive a speaker, especially if the amplitude is a little big, like oxymorons. This task offers a virtually unlimited range of difficulty. In 3 minutes, you will be able to produce a tone, but whoops are a little harder. Melodies are harder than that, but whoops are a little harder. Melodies are harder than that. So is keypad control. And you can surely imagine lots of grandiose possibilities, like a scheme that lets the computer memorize a melody entered at the keypad, or a drum machine. Need a cymbal? Perhaps a software pseudo-random noise generator would help. See text section 9.32. And okay. An easy way to let the computer output a chosen frequency is to let an output from the I/O decoder drive a MOSFET that drives a speaker. This you have done before, back in Lab 15, as you may recall, remembering the programmable divide by n counter. For higher volume, square the waveform with a toggling flip-flop before driving the transistor. On second thought, maybe we shouldn't be telling you how to make louder noises. Whatever you do with your little machine, don't forget to have fun. Great. All right, and here's a review of chapters 10 and 11, important topics: microcomputers, microprocessors, hardware, buses, 3-state to drive a bus, flops to take information off it, address decoding using control lines as well, for example, I/O decoding, partial address decoding, word byte transfers, bit input, pulse output. An occasional external event is best saved in a flip-flop, usually edge triggered with constant input. Pulse output, simple way. If pulse can be short, just use a decoder output. For longer pulse, need an output flop. Programming, branch on condition, loop iteration or delay, check bit, compare, looking for pattern, e.g. key check in Lab 22. Pointers, for speed, for table reads and fills. Need a way to tell whether the table is done. C, stack, it works so automatically that you seldom need to think about it. You do need to appreciate the difference between a subroutine call, useful for multiple use of one patch of code, and garden variety branch or jump. D, exception response. This is much less important for our purposes, but it is not hard to understand once you understand the use of the stack in an ordinary subroutine call. All right, and then we've got jargon and terms for the last chapter. Okay, these two chapters are especially rich, especially annoying in their use of acronyms. It's hard not to imagine that the manufacturers sometimes start with a clever acronym and then demand that the research department invents something to fit it. Riot, for example, an old chip that included RAM, I/O, and timer. Which came first, the riot or the chip? So this list of terms includes some substantial notions and some terms that are no more than names. Absolute addressing, access time, asynchronous bus, DTAC, EPROM, EPROM, exception, interrupt, PROM, RAM, ROM, vectors. I thought there was going to be a long list. It's not that long at all. Then we're up to our appendices. We've got Appendix A, equipment and parts. Okay, what have we got? What have we got? Tektronix. Oh, I see. Oh, I see. They're not going to tell you where to buy the parts. They're just going to tell you which parts you could get. Oh, I see. Diodes, LEDs. Okay. This was the scope they used, the Tektronix 2225. Dual channel, 50 megahertz. Oh, that's fun. DVM, 3.5 digit. It's pretty wussy by today's standards. Even my cheap DVMs have more than 3.5 digits. All right, we're off with other components. Various JFETs. All right. Some data sheets here for different bits and pieces. Very good. Wow. Information about the CPU they used. Write-only memory. Schematic of a lab microcomputer with the 68,000 CPU. Okay, we've got pinouts, transistors, ICs, gates. Cool. Must be nearly at the end. We are. Here it is, the index. Super. Now we're at the end. Wow. Okay. Let me throw you over to the farewell cam and we'll wrap up. And that's a wrap. So that was just a quick look through this old book. It looks like it was printed in 1999 and published originally in 1989. So it does meet our criteria as an old book, and of course it's just a quick look at the past before we get stuck into the future. So I thought I'd get that out for you today. Also, some stuff's arrived, which is good. Means I can get on with another project I've been doing. I might do that now, in fact, and then you'll see these videos come out this week. Yes, the learning the art of electronics is delayed, but there's other things to keep you interested in the meantime, not this video, of course. So congratulations if you made it all the way to the end. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.